So this is the third screencast on air pollution. And in this screencast, I'm first going to again look at the sources of air pollution and look at some of the data on air pollution. So air pollution comes from both natural sources and human causes. So first, let's look at the natural sources of air pollution. That includes volcanoes, which produce lots of sulfur dioxide, carbon monoxide, the nitrous oxides, and particulate matter. The second one is lightning. Lightning actually produces the nitrous oxides because remember there's so much nitrogen in the atmosphere that the energy from the lightning can convert it and have it combine with the oxygen in the air. A third source is fires, particularly forest fires that can occur naturally, and that produces carbon monoxide, particulate matters, much if you think of the ash in a campfire, and can also produce some nitrous oxides because there's nitrogen in the trees. There are even plants that can produce air pollutants. So as shown in the picture on the right here, some mountain ranges such as the Smoky Mountains have that natural haze to them that comes from the trees there releasing something that is a pollutant, something that is considered a pollutant because it's present in high enough concentrations to cause harm to other living things. Okay, so now we're going to turn our attention to anthropogenic or human-caused causes of air pollution and some numbers on them. So, the EPA studies air pollution and in particular produces data on the following sources of air pollution. First is on-road vehicles. That means all your cars and trucks. Second, power plants. Those are the plants that produce power or energy such as electricity. Next, industrial plants or industrial processes. And last, waste disposal. So let's look at some of their data on the next slide. These are not numbers for you to memorize. Again, we want to notice the trends as you did in the previous table. So we have carbon monoxide here, nitrogen oxides to the right. On the bottom left, sulfur dioxide and particulate matter, very tiny particulate matter, the PM less than 2.5. So we'll start up here with carbon monoxide, and you can see on-road vehicles comprise over 40 million metric tons of carbon monoxide produced by those cars or trucks. The next category, which is also a significant source, are non-road equipment. So what does the EPA mean by non-road equipment? Well, as far as I can tell from their website, they mean agricultural equipment, agricultural things like the harvesters. It also appears to include trains and mining equipment, which can be super, super, super large structures that are like moving trucks that are the size of a building. So those are the two main sources of carbon monoxide, and you have other categories down here. You notice there's one saying fossil fuel combustion, which is what on-road vehicles and non-road equipment are doing. As far as I can tell, what they mean by fossil fuel combustion in this graph is that it is fossil fuel that is used to form fertilizer. So when methane is used to convert nitrogen into nitrogen fertilizer, nitrogen from the air rather, into nitrogen fertilizer, that would count as fossil fuel combustion. So the second category here is for nitrogen oxides. Again, on-road vehicles, a significant contributor to nitrogen oxides, over 5 million metric tons. Non-road equipment, again, coming in a close second. And electricity generation, particularly from coal-burning power plants, is number 3. The other processes are down here. The third major air pollutant shown is sulfur dioxide, and the big cause of pollution here is electricity generation. That's mostly because of the coal-burning power plants, which contain coal is the dirtiest pollutant the dirtiest energy source. One of the reasons is because it does contain a lot of sulfur in coal. And moving last to particulate matter, it's a little more evenly distributed, but you can see road dust is very high, industrial processes not far behind, and electricity generation not far behind either. Oh, another source that I forgot to mention that I believe is part of this non-road equipment would be shipping. Shipping is also uses a lot of fossil fuels and would have a similar impact. Okay, so the next section will be looking at some processes and their complexity. And I don't expect you to memorize the complexity of these processes. I just want you to have an understanding and why it can be difficult to remediate these sources of pollution. So first we're going to look at the topic of smog. Think of smoke and fog, the word smoke being the SM and fog being the OG. You do need to know you do need to know the vocabulary term smog and its definition, and that ozone is a key example. But the rest of this is background information. So smog, the definition is it's a mix of photochemical oxidants. Let's break down that word and particulate matter. Photo means in the presence of sunlight, chemical in the presence of certain chemicals, often oxygen or water. And oxidants are things which remove electrons. And particulate matter we've defined before. So smog is a mix of photochemical oxidants and particulate matter. It causes a haze, which reduces sunlight and harms respiratory systems. There are different types of smog depending on their constituents. There's brown, gray, and atmospheric brown cloud. In Los Angeles, we have the one that's called brown smog, and that is sunlight which has acted on nitrogen oxides or sulfur dioxides or volatile organic compounds to form photochemical oxidants, of which ozone is one. So in a subsequent slide, we'll look at how that process unfolds. And photochemical smog, as you might imagine, is still a problem in the United States. In fact, I have a picture here of Los Angeles. There we go. And you can see the way the brown smog looks. Now, London's fog is actually called a gray smog. It has a more gray look to it. It also contains sulfur dioxide, and it usually contains other sulfur compounds as well. Coal was a really big and continues to be a big source of energy for London. And the way that the topography is around London tends to trap the air pollutants, and we'll look at that in a few slides. And the last one is China's air pollutant, which is called atmospheric brown cloud. It does look sort of brown like Los Angeles. It's a mixture, again, of particulate matter and ozone, and it also has carbon and nitrogen dioxide in it and covers huge areas. You might remember the last Olympics, China actually shut down many, many factories to clear the air so that the Olympics wouldn't be, the Olympic athletes wouldn't be impacted by all of the smog, and also so that it would look better. So that's something you probably remember. Okay, so here we have a complex chart about photochemical smog formation. Again, you do not need to memorize it. Just let me walk you through two situations. One here where there's only nitrogen dioxide, and the second one, a situation where the atmosphere contains nitrogen oxides and volatile organic compounds, and the results are different. So in the first diagram, you have your nitrogen dioxide in the atmosphere, and sunlight causes the reaction or energizes the reaction between the nitrogen dioxide and oxygen from the atmosphere. So one of the two oxygen atoms on the nitrogen dioxide is removed from the original molecule and joins O2, the oxygen that you breathe. That produces O3, which is ozone. Okay, now that's in the presence of sunlight. So when the sun goes down, when it's nighttime, and you have that ozone, that O3, and the nitrogen monoxide, it can go through another chemical reaction where that one oxygen atom then rejoins the nitrogen oxide and forms nitrogen dioxide and leaves behind O2, the oxygen that you breathe. Now, that process can be interrupted by having VOCs also in the atmosphere. So you have the first reaction, which is the same, ozone is produced. But then you have this nitrogen oxide floating out there, and it combines with volatile organic compounds, and then it forms photochemical oxidants other than ozone. And the problem there is that when the sun goes down, the ozone can't find the nitrogen oxide to recombine with to form the nitrogen dioxide and the O2, so it's stuck there in the atmosphere, and you have a positive feedback loop where the amount of ozone and the amount of other photochemical oxidants just continues to increase and increase each day. Okay, we'll wrap up this recording by taking a brief look at another process called a thermal inversion. And these thermal inversions. So we'll look at normal conditions shown in the diagram on the top and thermal inversion conditions listed on the bottom. So normally, as you go up through the atmosphere, the warm air becomes cooler and cooler and cooler. So as you go up a mountain, it gets colder. And that's a normal condition. But sometimes there's a situation where a warm layer of air, which is at mid-altitude, so right here, covers a layer of cold, dense air below it, shown here. So the warm inversion layer traps the emissions, the pollutants, that then accumulate beneath it. This happened in China recently. Let's see, when was that? Well, very recently, in a city called Tianjin. They had shut off the central heating system, and then there was a cold spell, and people started using coal stoves, individual coal stoves in their houses, and then that released carbon monoxide and particulate matter into that cool, trapped air, and 1,000 people became sick and 11 people died. There was an even worse situation in London a number of years ago, back in 1952-53 era, and it actually killed thousands, particularly the young, the elderly, and those with respiratory conditions. And some leading medical journals feel that there may have been even more than that. Okay, so that's a wrap for this third screencast, and we'll move on to a fourth.